We created the Sunulator to help people answer the question, is solar worth it?
Hi, I'm Andrew Redaway from the Alternative Technology Association. This video is on Sunulator, our free solar feasibility calculator. It's part of a series, and this video is looking at the results out of Sunulator. So obviously there's no point running it if you're not going to get something useful. So hopefully you will. Now, after we've run Sunulator and clicked on the quick information sheet, it takes us straight to the introduction. And you can see there's in the menu here there's several sheets of results, so we'll just click next to take us to the statistics. Now there's quite a lot of statistics in this sheet. Some of them may not be relevant, but I'll take you through the key ones anyway. The first section is just giving us a rundown on some of the inputs that we chose. For example, the horizon and the financial discount rate that we covered in the cost sheet, and the community ownership option, which we also chose in the cost section. And these are all consumer owned, so the solar system has been paid for by the electricity consumer who owns the building, and that same electricity consumer will be enjoying the bill savings into the future. With some of the other options, there's an investor involved who's paid for the solar system and will get a return on their investment through energy sales or loan repayments, for example. So when you see some of these reports, they may be specific to the energy consumer or the investor, but in this case it's only the consumer that we're interested in, because we don't have any investor involved in any of these scenarios. Because Sunulator was originally developed for community solar projects, when it talks about a community group, and then that's basically the same as the investor. Alright, so the first result is the environmental section, and we touched on this with the in the quick results sheet. It gave us the equivalent number of cars off the road, 1.6 cars off the road, 5.6 tons of carbon dioxide offset annually, and slightly less for the battery options after you allow for the additional energy that has to be consumed to make up the losses in the battery. And the green shading has all gone on the scenario without a battery, the 4 kilowatt one, because that's got the best environmental credentials there. Now, you may be thinking, but surely batteries have some environmental benefits too. And yes, they do, but it's more of just a long-term effect at this stage. If you are installing batteries, then you're an early adopter who's helping to break new ground to develop the industry and build economies of scale for the battery installers and the battery manufacturers, etc. But as a direct environmental benefit, there's in most cases for a grid connected system, which is what Sunulator is concerned with, there's really no direct environmental benefit. Okay, some statistics on the system sizing. Again, we saw this in the quick results. So the self-consumption of solar generation, that's what proportion of solar generation is used on site rather than being exported out to the grid. With no battery it's 33%, small battery 48%, big battery 65%. So having a battery helps you to use more of your solar generation yourself rather than exporting it. which is good because that's good to see that, and because that's the reason why most people are installing batteries in their solar system. And battery utilization is the average daily discharge of the battery as a percentage of its usable capacity. So the larger battery is not always fully discharged, because there are some days when it may not get enough charge, or there may not be enough consumption in the evening to fully discharge it. Well, we can look at that in more detail later on. Okay, let's get into the dollars and cents. So this is for the energy consumer. So the upfront investment, we saw that in the cost section, 5,600 just with the solar system, and then when we add on the battery, that's going up depending on the size of the battery. So highlighting the one with the cheapest upfront cost. Now the annual electricity cost, so that's the electricity bill for business as usual, $1,570. With a solar system dropping to $900, and then we have further reductions with the batteries. So your smallest electricity bill is for your solar system with the big battery. And that number just repeats down here. Under some scenarios, you might have allowed for a maintenance costs on your solar system, for example. Okay, so now the next section is looking at more statistics, financial measures compared to your business as usual. So what's your cost saving of your solar battery system compared to business as usual? $668, $789, and $928. So yeah, obviously your bigger battery system has given you the biggest dollar saving. And then we have that as a percentage terms as well. Now we get into some of the more technical financial measures. So the net present value, what that does is it takes into account all of your future bill savings going out for 20 years, and also all of your future costs for your replacement of your equipment and your maintenance if we'd allowed for that, etc. And it basically adds them all up and says, here's your net position right now in today's dollars for the project. So this $3,015, it's saying this project is going to deliver you over 20 years. It's going to deliver you $3,000 of value in today's dollars, and taking into account all of those costs and bill savings. Your system with a small battery is going to deliver you a smaller net present value. That's because the upfront cost is bigger, and your large battery comes out with a negative net present value, because your additional bill savings from having that larger battery are small compared to the additional upfront costs that you incur. So this is one way that projects are often compared and evaluated when you're deciding whether to go ahead with a project or not, is the net present value. Now the payback period, I'll just say the net present value also takes into account that discount rate that we mentioned in the cost section. So benefits and costs further out into the future will have less of an impact on this number than benefits and costs early on in the horizon. Okay, simple payback period. So payback period is, most people are familiar with that. You spend some money up front, and then we're going to get bill savings. So when will those total bill savings exceed your upfront cost? How many years do we have to wait to consider that our solar system has paid for itself? So we've got 9 years, and then 16 and 19. So the even though you get bigger bill savings with the battery, it takes you longer to pay off because of the higher upfront cost, because the bill savings are not dramatically bigger. You can see we're going from a 42% with no battery up to a 50% with bill saving with a small battery. Even though this is called simple, it still does take into account degradation of the solar panels over time. So they're going to not generate quite as much each year into the future as they get older. And it also takes into account that equipment replacement. So in year 11, we're going to incur a cost to replace the inverter and the battery, which is one of the factors that makes these numbers with the battery bigger. So once you go beyond 10 years, it often jumps out fairly dramatically after that. The discounted payback period is the same, but it now also takes into account that discount rate as well. So benefits further out in the future again count for less than what they would if you didn't include that discount rate. Normally we would prefer to use the discounted rate, because if you don't, then it's not really a fair comparison, because if you decided not to spend that money on the extra battery, for example, you could have put that money, you could have paid off your mortgage quicker, or you could have put it in the bank and earned interest. So for a fair comparison, you have to take that into account as well. Return on investment is using the internal rate of return calculation, which it's kind of like the net present value, but it's working out an equivalent interest rate for a financial investment. So we're saying a 7.8% return on investment for the solar system with no battery. So you could use that as like a comparison rate against putting your money into a term deposit at the bank that paid you 7.8%, and there was no tax on your interest. And because with the solar system, there's no tax on your bill savings. Because of the upfront cost going up, then we get a lower internal rate of return for the battery systems. Now, those are all coming out less favourable for the battery systems, and it's really because batteries are still quite expensive. So it would be interesting to see what will happen once battery costs come down. We're expecting prices to drop by about 10% per year or so. So that's one of the things that you can do in Sunulator. We've got our upfront solar battery investment there. On the cost sheet, you could halve those battery costs, for example, and start to see at what point it becomes attractive in your situation. Levelized cost of energy is a bit of a technical one. It's just like it's like an equivalent grid tariff that you're paying to get electricity out of your solar system. So it's typical in Australia. You might be paying between 20 to 30 cents per kilowatt hour to buy electricity off the grid, and we're getting cheaper electricity than that for our solar systems. Now the next section is for an investor that is not relevant because we've chosen to go consumer owned for all scenarios. So we'll just skip over all of that. And now we're getting into some of the more detailed stats that you might want to look at if you're trying to understand what's happening with the solar system and why some numbers are the way they are. I won't go into too much detail here. The first table is for energy, so average daily kilowatt hours. So we're consuming 15 kilowatt hours a day. That's not far off the Australian household average. Just a reminder, we've used real metering data from an Australian household here, but households vary dramatically over how much energy they use and also what sort of patterns, and all of that will have an impact on the results. Generation, so the solar system is generating just about slightly more than your consumption every day. Of course, that's going to vary from summer to winter, cloudy to sunny, etc. Some stats here on how much your battery is getting charged and discharged, how much is getting exported out to the grid. Alright, there's a section here on maximum demand in kilowatts. So it's the maximum import from the grid, which can be important, especially if you were on a demand tariff or you were considering switching to a demand tariff. And interestingly, that's all happening early in the morning. There's a spike in electricity import going to up to 5 kilowatts. So yeah, interesting appliance consumption use there. For some data sets, you might see a daytime spike which gets reduced by your solar systems and your solar battery systems. In this case, they maybe had a big party on the 15th of March or something, which is so they max of the morning, and it hasn't been able to be covered by the solar or the battery on that day. And then we get into costs. So like how much you're paying per day for your energy and your standing charges and all that stuff, and how much you're earning per day from a feed-in, from how much electricity you're feeding into the grid. So you're exporting more into the grid without the battery, which is going to earn you some extra money as well, which is worthwhile taking into account when you're weighing up what sort of size battery to include. So that's the statistics sheet. Now we'll click on next. This sheet is full of charts, and it's all about it's not looking at the dollars. We'll come to that on the next sheet. But this one's charts to help you understand what's happening with your energy consumption. And you can choose which report from a big list in the drop-down box here. The first 4 are all like charts showing you what's happening over a day, half hour by half hour. So this is export and import to or from the grid. So the blue one is your business as usual, where you've got no solar and no battery. So that's just how much electricity is being consumed, and it's an average over all dates in the entire year period that we've simulated. So this is your average consumption profile. We've got a morning peak and an evening peak, just based on the data that we've imported into Sunulator. Now the 4 kilowatt system with the red, it's all the same until the sun comes up, and then suddenly we're reducing our import, and now we're exporting. So during the middle part of the day, we're exporting electricity to the grid, and then around 5 p.m. we're importing again. With the battery, with a smaller battery, the curve looks mostly similar to the red one, but now we're putting electricity into the battery, so we're not exporting as much. Some of that energy that would have been exported is getting soaked up into the battery instead. By this stage, the battery's full and the curves are the same. And now, instead of importing from the grid, we're getting some of that energy discharged out of the battery to meet consumption in the house. So yeah, at a glance we can see roughly on just an average pattern over the whole year that the battery does seem to be doing what it's intended to do. The purple line here with the crosses is with the larger battery, so it's doing the same thing, but just a bigger effect. So we don't start exporting to the grid until 10:30 a.m. in the morning, and then our exports are all reduced up until the late afternoon, and then imports during the evening are reduced quite a lot. Now I've built in a nice feature here. You can either click on the date and choose a particular date in the whole year period that you want to look at in detail, or we can just click on this button, next date, and it'll move us to the it's moved us to the 2nd of January. So now we're looking at one specific day, and you can see the lines are not so smooth anymore. It's not averaging out over 365 curves. It's a specific curve that it's simulated. Excuse me. It looks like we've got low electricity consumption, so the households on holidays perhaps. We've still got quite a lot of solar generation. We can jump ahead a whole month and get out of that holiday period. This is interesting. So if we look at the red line, we don't have a nice sort of upside down bell shape here. It looks like it's a cloudy day, so our solar generation is a bit up and down. But again, you can see the batteries are doing what they're meant to do. So if I just scroll through a few days, you can start to get a feeling of the amount of variability that you can see in the energy patterns on from day to day. Just put that back to all. And if you did want to investigate a specific day, then you can do it with this chart. So that's a grid import and export. The next one is the battery state of charge from 0 to 100%. So business as usual, and the 4 kilowatt with no battery are just on the x-axis. With the small battery, we're generally averaged out over the whole year. It's charging up fast. It's able to achieve almost a whole charge by early afternoon, and then it starts discharging. With the larger battery, we can see that it takes longer to fill up because it's bigger. It's got a bigger capacity, and it takes longer to fully discharge as well. And in fact, it looks like on average we've still got a bit of energy in the battery in the early hours of the morning. So if your aim was to try and minimize your use of the grid, then the bigger battery would be the way to go. And again, we can scroll onto specific days and see what's going on. So here the battery's full, and it stayed full all that time on that specific day. I'll just scroll through a few days. Maybe I'll go out of the holiday period. Alright, so we're starting to see some days here where the battery did not achieve 100% state of charge. It only filled up partially and then discharged. So you can see that variability I was referring to previously. Battery energy flows. This is again focusing on the battery, and it's just saying, well, how much energy is flowing in or out of the battery. And so the batteries are being charged in the morning, and then they're being discharged in the evening. Now, just one other chart I might show you. So after those four, it's not really the daily half-hourly view. It's more big picture. What's happening with your energy. So this one's total generation per month, and there's only one line because they're all generating exactly the same. They've got the same 4 kilowatt solar system included. But you can see here the difference between summer generation and winter in Sydney. So there's plenty more charts for you to play around with in the consumption and generation sheet, and yeah, feel free to play. Now if we click next, we get to the dollar impact sheet. So again, it's a whole bunch of charts that you can access through this drop down box. The first one is quite a useful chart that helps you visualize the economics of the project from the consumer's point of view. So the consumer has in year 0, which is when the investment happens, they've paid out, $5,000 to $12,000 to install this solar system, paying extra for the batteries, and then in year 1, they've received a bill saving, which is counting as positive, and then they're getting that bill saving every year until they achieve a payback, and they've got back to they're ahead on their investment in year 10. At that point, they have to replace the inverter, so that's put them negative again, and after that they keep getting their bill savings, and they're ahead on their investment again in year 14 or 15. So this gives you an easy way to visualize like how the payback period works, and also it also gives you an idea of the net present value. So you can see how far above zero this line gets to in around the 20-year period. If you look closely, you might also notice there's a slight curve on these lines. It's not just going straight with the ruler; it's curving over slightly, and that's due to the discount rate that I mentioned previously in the costs section and the results section. So future benefits, even though the bill savings may be increasing in dollar terms, we're not going to count them as highly, because a dollar that you save in the future is not as useful to you as a dollar that you get, in the first year or two of your investment. If we look at the solar system with the big battery, it doesn't achieve payback in year 10. It then gets hit with a replacement cost for not only the inverter but the battery as well, and it doesn't even achieve payback before the second replacement of inverter and battery. So yeah, it's pretty obvious that from a bill saving point of view, it's not a very attractive investment. Now again, there's plenty of other charts here. I might just show you this grid electricity bill cost monthly. So business as usual. So January to December, this is the what the monthly electricity bill would be based on the consumption and the grid tariff that they're on. So they're paying more for electricity in the summer months, presumably air conditioning, maybe some other higher activity levels in summer than winter. Maybe this household is using gas for heating and hot water, for example. With a 4 kilowatt solar system, those bills have dropped quite dramatically. Adding on a battery, the bills are lower, but not dramatically lower than the solar system with no battery. So and this is helping us to understand why the economics are favouring a solar system with no battery. And yeah, again, there's plenty of other charts there, but I won't go through them all. Hopefully you've the ones that I've shown you would be the most useful ones that you'd use to get a quick idea of your economic feasibility of your project and which scenario might be the most attractive. So that's it for this video. The final report is it's only relevant in a community solar project or where there's investors involved. So I won't cover it in this video. Thank you.